This lecture deals with another issue that we wouldn't take up in a normal version of Philosophy 170. It's a theoretical question. We've given ourselves 5 basic connectives to work with, but we might wonder, could we get by with fewer? Is it in principle possible to say everything that we can say with all 5 using less than all 5, using a smaller set? So the answer is we can do this. What it means, in other words, is that we can define some of the connectives in terms of others, and we can get started on that this way. We can define or using just not and and. We can define and using just not and or. In other words, we can find a well-formed formula that uses P, Q, not, and that means exactly the same thing as P or Q. It'll be more complicated to write, but it'll mean the same thing. Similarly, we could write a well-formed formula with P, Q, not, and or that would mean the same thing as P and Q. And once again, it would just be a matter of it being a little more complicated. But it would have the same truth table, the same row of 1s and 0s under the main connective. So I'd like you to pause the lecture before you go on and see for yourself if you can figure out how to do this. And it might be useful to think about this. And statements are true in 1 row, or statements are true in 3 rows. And so you might want to think about that when you're figuring out how to go back and forth here. So pause and start up when you think you've got the answer. Here's the answer. You can use a truth table to check it yourself. P or Q amounts to not P, and not Q. Not too hard to see why. P or Q means at least one of P and Q is true. The bracketed part here says both P and Q are false. If we deny that, that amounts to saying at least one part is true. Down here, P and Q, well, that means that both of them are true. The bracketed part here says at least one of P and Q is false. So when that's not so, they're both true. But what we've just seen is that in principle, we could get rid of the and if we wanted and just use the or. Or alternatively, we could get rid of the or if we wanted and just use and. In writing things, that isn't necessarily practical, but there might be other contexts where it is. And it's also an interesting thing to know about how these connectives are related and what our system calls for if we're going to look at the minimum requirements for getting things expressed properly and set up right. Carrying on, can we define the arrow using just not and or? Well, as you might guess, the answer is yes. Can we define the arrow using just not and? Once again, you might guess the answer is yes. So once again, pause and try. Find a sentence using not or P and Q that means P arrow Q. Find a sentence using not and P and Q that means P arrow Q. And you might keep in mind that an arrow sentence is true in 3 cases, and the denial of an arrow sentence is true in 1 case. So give that some thought, give it a try, see what you come up with. You can check that both of these work. This one should look a little bit familiar. If you remember what we said when we gave a justification for the table for P arrow Q, we ended up actually working with this disjunction. Not P or Q amounts to P arrow Q, and it's easy to check that using a truth table. This one's also not hard to see. The way to remember the table for P arrow Q, we said, was to remember when it's false. When's it false? When the antecedent's true and the consequence false. That's what we have in brackets here. If we deny that, then we've simply got P arrow Q. So there are various ways we could slim things down here. We could pick just not and, we could pick just not and or for that matter, we could define or in terms of if-then, we could define and in terms of if-then. We got these various minimal pairs. We haven't mentioned the connective double arrow yet. And if you think about it, and you can confirm this with the table, P if and only if Q amounts to P arrow Q and Q arrow P. If P then Q, and if Q then P is the same thing as P if and only if Q. So try this. See if you can find a well-formed formula, and here you got a few more resources to use, using P, Q, not, and or, that means the same as P if and only if Q. And then once you've done that, which is a little bit easier because I think you can see if you think about what this actually means, how to get there, find a WOOF that uses only the not and the and. That's a sort of exercise in manipulating these things. It still just means P if and only if Q. But pause the lecture here first, see what you can come up with, and then start again. Well, first you can check that this formula in square brackets amounts to P if and only if Q. Why? P if and only if Q says that P and Q have the same truth value. Either they're both true or they're both false. So that's not hard to see. Now what's gone on here is that we've taken this or statement here and we've rewritten it using just and. I'm not saying that this is just obviously correct, but a little thought should show you that it is, and you can always check with the truth table. Another way to do it would be this. This is perhaps a little bit more appealing. P if and only if Q means that P and Q have the same truth value. This says their truth values don't differ in this way, and their truth values don't differ in this way. So that's another way of saying that they have the same truth value and that P if and only if Q is true. So up to now, what we've shown is that we could get by with any of these pairs. Not an and, not an or, not an arrow. No matter which of these we picked, it would be enough to let us say everything we can say with the whole set of 5. Now you might wonder, could we get by with not and the double arrow? If so, how could we do it? If not, why not? Once again, you might want to pause and think about that. What's the answer to this question? Well, the answer is that we couldn't. And we won't go into this in detail, but briefly the reason is this. If we have just the not and the double arrow, there's no way to define and, there's no way to define or. More generally, there's no way to define a connective that's true in 3 out of 4 rows, like or, nor to define one that's false in 3 out of 4 rows, like and. You can't do either of those things. We could talk about why, but I'd like you to just kind of ponder that on your own. It's sort of similar to this fact. Any integer greater than 1 can be written as the sum of odd integers. It might be 2 odd integers, it might be 3, it might be a bunch, but you can write it as the sum of odd integers. But no odd integer is the sum of 2 even numbers or 4 even numbers or 3 or whatever. When you add even numbers, you always get even numbers. When you add odd numbers, that's not so. Now the next concept is a little bit different. It's called disjunctive normal form, but what I'm going to do is before we go on, we're going to pause, and then if you want to look at what we've talked about so far and feel you've got a good grip on it by reviewing it, go ahead and do that, and then come back, we'll pick up the idea of disjunctive normal form.